Hi everyone, it's time for us to explore everyone's two favorite units, gas laws and stoichiometry, and we're going to take a look at the intersection point between those two things. So a couple things to take note of. Number one, stoichiometry requires a balanced chemical equation because by definition, stoichiometry is going from one thing in an equation to something else. So you'll notice all four of the example problems below I've written a balanced chemical equation for. Before we dive into the example problems, you should pause the video and get some practice writing out a balanced chemical equation from all of the word equations that are given. And secondly, there's a little expression that we can exploit here, which is that at STP, so at STP only, 1 mole of any gas occupies 22.4 liters. But remember, this is only for a gas. Solids don't do this, liquids don't do this. This is only for a gas. At STP only, 1 mole occupies 22.4 liters. So that allows us to make something called a liter ratio or a volume ratio. But instead of trying to explain that first, I think it's easier to see if we do an example problem. So let's dive into number one. And you'll notice in number one, we have 1.78 liters of oxygen, 1.78 liters of this reacting. And we are interested in figuring out when that reacts with an excess of ammonia. So we know oxygen is not our, oxygen is our limiting reactant. We're going to run out of that first. We're going to use up all 1.78 liters. We want to know how many liters of this nitrogen can we make. That's our goal. And so this idea of going from one thing to another in a chemical formula, that is stoichiometry. Let's start out with 1.78 liters of our oxygen gas. So 1.78 liters of oxygen. And obviously, if we're doing stoichiometry, we need to ultimately get this thing turned into moles in order to convert to something else in the chemical equation. So we know that liters of oxygen has to go on the bottom to cancel out, and ultimately we need to get some moles of oxygen. And so the question is, do we know a conversion that allows us to go from liters to moles? And we do. And that conversion is that for any 1 mole of a gas, and oxygen is a gas, we can use this, there are 22.4 liters. And once we've done that, we know that moles of oxygen would need to go on the bottom, again to cancel out, and the question is asking us to convert into moles of nitrogen, moles of N2. And so where do we get those values? Well, we look to the balanced chemical equation. They have coefficients. You'll notice there's a 2 in front of nitrogen, there's a 3 in front of oxygen. And then finally, we don't just want moles of nitrogen, we want liters. So the question is, do we know a relationship that allows us to convert from moles of N2, which, by the way, is a gas, into liters of N2? And we do, right? We know that 1 mole of any gas occupies 22.4 liters. So when you've done it that way, you'll notice that liters of oxygen cancel, moles of oxygen cancel, moles of nitrogen cancel. And at the end of the day, when you solve this thing, you will end up with sig figs 1.19 liters of N2. So it looks a lot like stoichiometry. Instead of going from grams to moles, we've gone from liters to moles. But you keen observers might have noticed that this mathematical operation of dividing by 22.4 and this one of multiplying by 22.4 really didn't do much of anything, right? So here's the trick that we can use on this shortcut called the volume or the liter ratio. If your entire reaction is taking place at STP, which ours is, or the temperature and pressure is constant, which is really the case for this one, that means that the relationship between temperature and pressure, and therefore between liters and moles, is the same for all parts of the reaction, right? So that means that the ratio between any gas, between its liters and its moles, and any other gas between its liters and its moles, is going to be the same. And so you can really just eliminate that part of the dimensional analysis if you have things taking place at constant temperature and pressure. So you could write it out this way: 1.78 liters of O2. You know that because this is a gas at constant temperature and pressure, the number of liters of oxygen is going to be in some relationship to the number of liters of nitrogen, and that is based off of their coefficients. There's a 2 in front of O2, there's a 3 in front of N2. Sub that backwards, sorry, there's a 3 in front of O2, 2 in front of N2. We know we can cancel out liters of O2, When you do that math, you will again be left with 1.19 liters of N2. So you can just get there a little bit more efficiently. Let me zoom out and show you that entire thing in action. So again, you don't have to do what I did in purple. You may absolutely all the time do what I did in green to be sure of yourself. But if you run into a reaction at constant temperature and pressure or at STP, where the entire thing is at STP, you can use that trick. Let's compare and contrast that with what we see in number 2. So in number 2, here's what we're told. We're told that we have 5 liters of dinitrogen pentoxide, and we're furthermore told that that is at STP. So let's write that in here. We have 5.00 liters of this, and it is at STP, which means if it's at STP, we can exploit that liter to mole ratio. We are then asked what volume of nitrogen dioxide is present, but it is measured at 64.5 degrees Celsius and 1.76 atm. So is this one at STP? No, it's not. So this part of it is not at STP, which means, first off, we can't use that liter or volume ratio. But we'll explore what to do when we get there. So let's start with what we know. We know 5 liters is what we have of this N2O5. So we're starting off with 5.00 liters of N2O5. We're still doing stoichiometry, right? Because at the end of the day, we want to convert from one thing to another in the balanced chemical equation. So we know we need to do stoichiometry. To do stoichiometry, we need to use moles. For N2O5, remember N2O5 is at STP, right? We were told right there it's at STP. So that means that for N2O5 at least, the relationship between liters of N2O5 and moles of N2O5 is something that's very straightforward. We know that 1 mole has a volume of 22.4 liters, and that works here because we are at STP. And if we have moles of N2O5, we can put that downstairs to cancel out with moles of NO2. And we know that the relationship there is based off of the coefficients. There's a 2 in front of N2O5, there's a 4 in front of NO2, and just as a reminder, we're going to write that out as 4 and 2, not simplify it, just so we can see where your work came from. And when you do that math, you'll figure out that you have a number of moles of NO2, and it is 4.446 moles of NO2. And so some of us might be wondering, well, wait a second, why didn't we just go to 22.4 liters? But remember, because why would we do that? Well, we're looking for a volume, but remember, we're not at STP. So the relationship of 22.4 liters per mole is only true for gases, and it's only true at STP. So we can't use that, but we do need to get to volume, right? So volume here is our unknown. We're looking for a volume. If only we had some other information, and we do. The problem tells us, if you look above, that the pressure is equal to 1.76 atm. We just solved for moles, so that is N. We are given a temperature of 64.5 degrees Celsius. We're doing gas laws here, so this has to be Kelvin. We'll turn that in by adding 273.15. We'll get 337.7 Kelvin. And I don't know about you, but I'm starting to recognize that we have all of the variables for a PV equals nRT problem, right? So we could use the ideal gas law, which is that PV equals nRT. We're interested here in a volume, so we want ultimately nRT over P. And we can plug in everything we just found, right? We know that the number of moles is 0.446 moles. We know R is 0.0821 liters times atmospheres over moles times Kelvin. We know that there's a temperature involved. It's 337.7 K. And we're putting all of that over our pressure, which is 1.76 atm. So let's take a look at our units. In the numerator only, we have moles on top, moles on the bottom. We have Kelvin on the top, Kelvin on the bottom. In the very top here, we have atm. In the very bottom, we have atm. That means the only unit we have left over is liters. And so if you solve this, it's good that you have liters because you're looking for a volume. You want 3 sig figs, you can get 7.01 liters. So just to kind of summarize what we're doing in number 2 versus number 1, notice in number 1, the whole thing takes place at constant temperature and pressure, which means that the relationship of 22.4 liters, or really any volume to mole ratio, is true, which means we can kind of just cut it out of the equation like we did here. But in number 2, only one piece of this happens at STP, right? So only this portion happens at STP. The second half does not, so we have to bring in PV equals nRT into play, but at least we used what I did in green to get to moles. Okay, let's try some other examples with different applications. Let's look at calcium oxide being produced from the decomposition of calcium carbonate. So here, we are told that we're going to start with 152 grams of calcium carbonate, and we're interested in how many liters of CO2 we can make. And by the way, it says that CO2 is produced at STP. So that's kind of an important clue that we're going to be doing this thing at STP, and that might help us out. Now, we have 152 grams of calcium carbonate. So let's start there, 152 grams of CaCO3. And some of us might be wondering, well, is this at STP? Can we use 22.4? Remember, 22.4 only works for liters per mole. We have grams, so 22.4 isn't really useful to us, right? And you might ask, well, could we use the density to get to liters? And maybe, but also an issue is that calcium carbonate is a solid. This is like a solid powder at room temperature, right? So we're not going to be doing this with 22.4. That only applies to gases. But there's another trick up our sleeves. We know we're doing stoichiometry because at the end of the day, we're going from one thing to another in our balanced chemical equation. And we know that there's a relationship that we have to get to, which is moles. And it turns out that you know the number of grams of calcium carbonate in a mole of calcium carbonate. And where does it come from? Well, it comes from the periodic table. And so you can figure out the molar mass of calcium carbonate, add up 1 calcium, 1 carbon, 3 oxygens. I've done it for you to save time. It turns out it's 100.09 grams of calcium carbonate in every mole. Now that we have moles, that's a great place to be because we can go from moles of one thing, in this case calcium carbonate, to moles of our other thing, in this case we want carbon dioxide. We know we can get those values from the coefficients of our balanced chemical equation. In this case they are both 1s, so it's just a 1-to-1 ratio, but we still write it to show that our units are canceling. And then we need a way to get from moles of CO2 to liters of CO2. Because ultimately, at the end of the day, right, we were asked for a volume. And you might say, well, I don't know like the molar volume of CO2, right? It's not a mass I can find on the periodic table, but it's a gas at STP. So 1 mole of any gas at STP is 22.4 liters. And so that relationship is really useful to you, obviously, as you're solving stoichiometry problems with gases. Notice that grams of calcium carbonate cancel, moles of calcium carbonate cancel, moles of carbon dioxide cancel. At the end of the day, when you do this math, you will want 3 sig figs, and you will get 34.0 liters of CO2 from this reaction. All right, let's try one more. In number 4, we're looking at oxygen gas. We're trying to generate out 5.00 liters of oxygen gas. You'll notice that we're measuring that at STP, so that's important. This at STP is taking place for oxygen gas. That's useful for our 22.4 liters. In this case, we want to know how much potassium chlorate do we need, and in particular, we want a mass, right? We want to know how many grams of this do we need. And so another thing to just keep in mind here is we're looking for a mass, but also this is a solid. So just bear in mind that the 22.4 isn't going to work for potassium chlorate. But we shouldn't start there anyway because we've been given a number for oxygen. So let's start with that 5.00 liters of oxygen. Start here. And we need to start figuring out how to get from one thing to another, right? And the way you do that in a chemical equation is in the unit moles. So do you have a relationship for a gas, in this case oxygen, at STP to go from liters to moles? Well, you do. You know that 1 mole is equal to 22.4 liters. And once you have moles of O2, that's a great place to be because you know that using a mole-to-mole ratio from your coefficients is going to allow you to convert from one thing, in this case oxygen, to another, KClO3, using the coefficients. And you'll notice there's a 2 in front of KClO3 and a 3 in front of oxygen. Once you've done that, you have moles of KClO3, so you've done good work because you're now in the right label, right? At the end of the day, we want some unit of KClO3, but unfortunately we want grams of KClO3. There's no easy way to do that like a gas law 22.4 type number, but you do have a periodic table. So you could add up 1 potassium, 1 chlorine, and 3 oxygens. And if you do, you'll find a mass of 122.55 grams of potassium chlorate for every 1 mole. You'll notice that our liters of oxygen cancel, our moles of oxygen cancel, our moles of potassium chlorate cancel. At the end of the day, with sig figs, you will be left off with 18.2 grams of potassium chlorate required to give you those 5 liters of oxygen that you're looking for in your reaction. And just a reminder, we did a demo earlier in the year where we had a gummy bear meet an untimely demise, and our oxidizer was KClO3. This is about what we did, right? So we had somewhere in the neighborhood of 20 to 30 grams of potassium chlorate that we decomposed. And so we made 5 liters of oxygen to pump into this reaction with our gummy bear and make it combust rather violently.